Welcome to The Explainer. Today, we're diving into one of the most awe-inspiring structures on our entire planet, and we're going to use it as a sort of giant case study to understand the fascinating hidden mechanics of volcanoes. We are demystifying Mauna Loa. This is the undisputed heavyweight champion of active volcanoes. So let's get right into it. All right, Section 1, Meet the Sleeping Giant. When we use the word giant, we really aren't just throwing around a colorful adjective. We are talking about a structure that literally bends the Earth's crust under its own weight. Just wrap your head around this staggering number, 56,000 feet. Now, you might look up at Mauna Loa's summit in Hawaii and see it cresting at about 13,679 feet above sea level. But here's the crazy part. That is literally just the tip of the iceberg. Its massive bulk actually depresses the seafloor beneath it by another 5 miles, pushing it down into the shape of an upside-down mountain. When you measure Mauna Loa from its true base, deep down within that depressed ocean crust, all the way up to its summit, it absolutely dwarfs Mount Everest. It is, hands down, the largest active volcano on Earth by both mass and volume. But here's the thing, Mauna Loa isn't just some static stone monument. It's a living, breathing geological engine. And that brings us to the whole reason we're investigating this today. Why did this absolute giant suddenly wake up back in November of 2022? From 1984 up until 2022, Mauna Loa was actually in its longest quiet period in recorded history, a 38-year slumber. And then, out of nowhere, the glowing lava returned. So to understand exactly how and why a wake-up call like this happens, we first have to understand how a mountain like this gets built in the first place. Which leads us nicely into Section 2, the science of shapes. Have you ever wondered why some volcanoes look like these incredibly steep triangles that just violently explode, while others are these massive, flattened-out domes? Well, it all comes down to one absolutely crucial concept: viscosity. Viscosity is basically just a fluid's resistance to flow. Think of it as the stickiness of the magma. It's like the difference between pouring a glass of water versus trying to pour thick, cold honey. Magma viscosity is really the secret architect here. It's the single most important factor that dictates whether a volcano is going to build up into a steep cone that traps gas and eventually blows its top, or if it's going to form a massive, sprawling mountain where the lava just travels for miles. So on one side of the spectrum, we have shield volcanoes. That's what Mauna Loa is. They are up this really thin, runny, basaltic lava that has super low viscosity. And because that lava is so incredibly fluid, it spreads way out from the source, creating these really broad, gentle slopes of less than 10 degrees. But then on the flip side, we have stratovolcanoes. Now, these erupt highly viscous, sticky magma. That lava is so thick, it can't flow easily, so it just piles up around the vent. And as it piles up, it traps all these expanding underlying gases until, boom, you get a steep-sided, incredibly explosive eruption. Building on that idea, the composition of the magma generally gives us 4 main types of volcanoes here on Earth. We just talked about our gentle shield volcanoes and those steep, explosive stratovolcanoes, also known as composite volcanoes. But to round out the picture, we also have cinder cones. These are usually smaller, circular structures built from fragments of blown-up lava, which is called scoria, and get this, they usually only erupt once. And finally, we have lava domes. This is where the lava is just ridiculously thick. It's so viscous, it barely flows at all, so it literally just piles up into a steep little mound right over the vent. All right, moving on to Section 3, inside Earth's largest volcano. So, back to Mauna Loa. How did it get to be so unfathomably large? 2 words: Hawaii hotspot. Deep down in the Earth's mantle, there's the stationary thermal plume. And as the Pacific tectonic plate slowly drifts over that stationary hotspot, the plume constantly feeds magma up to the surface. It is honestly mind-blowing to think about the timescales involved here, but Mauna Loa has been sitting near this hotspot for anywhere from 700,000 to 1 million years. Because its magma has that low viscosity we talked about, it has spent hundreds of thousands of years continually painting layer after fluid layer of basaltic rock, just slowly building up the sprawling giant we see today. Now, if you were to travel to the very top of Mauna Loa, you actually won't find a pointy peak. Instead, you'll find a massive feature called a caldera. Basically, a caldera forms when a huge eruption empties out the shallow magma chamber right beneath the summit. And because it's empty, the roof literally collapses inward. Mauna Loa's summit caldera is named Mokuaweoweo. It's an immense depression. We're talking roughly 6.2 by 2.5 kilometers across, and it actually collapsed into the form we see today somewhere between 1,000 and 1,500 years ago. Okay, so I know I just made a big point about how shield volcanoes aren't really known for violent explosions. But you know what? Geology loves a loophole. Mauna Loa is so incredibly tall that back during the last ice age, roughly 15,000 to 25,000 years ago, it actually had glaciers at the summit. And when scorching hot magma abruptly meets frozen glacial ice, you get what is called a phreatomagmatic eruption. The water instantly flashes to steam, causing highly explosive blasts that produce thick ash deposits. It's a complete wild departure from Mauna Loa's usual gentle lava flows. That brings us to Section 4, Living in the Crosshairs. When we shift our focus over to the human element, we see that for centuries people have had to navigate the dual nature of Mauna Loa, its incredible sacredness and its extreme danger. Ancient Hawaiians established the incredibly arduous Ainapo Trail, where they would ascend miles up the volcano to leave offerings and honor Pele, the volcano goddess, deeply connected to this powerful landscape. But that threat is always there in the background. Take 1950, for example. A massive eruption sent incredibly fast-moving lava rushing down the mountain. It reached the ocean in just 3 hours, permanently destroying the village of Hokunamalka along the way. That runny shield lava, it can be absolutely devastating when it moves that fast. And this actually leads us to one of the most incredible historical stories I've ever come across. It was 1942, just months after the attack on Pearl Harbor, and Hawaii was under a very strict wartime blackout. Suddenly, Mauna Loa erupted, and it completely lit up the night sky. The U.S. government literally issued a gag order to the press. They were terrified that this glowing lava would act as a giant glowing beacon for Japanese bombers. And when the lava actually started threatening a vital water supply, the U.S. Army Air Force flew over and literally dropped high explosive bombs directly onto the lava flow to try and redirect it. I mean, just wild stuff. Bringing this dynamic threat right up to our modern day, just think about the staggering speed of that 2022 eruption we mentioned earlier. So, on the night of November 27th, lava breaches the summit caldera. By the very next morning, the eruption has already migrated down to the northeast rift zone, ripping open massive fissures. By that evening, fast-moving lava has completely cut off the main road to the Mauna Loa Observatory. And within 2 weeks, by December 13th, the whole event is just over. It perfectly highlights how insanely quickly this giant can wake up and alter the modern landscape. And finally, Section 5, Watching and Waiting. So, considering the speed and scale of these eruptions, how exactly do we protect the people living nearby today? Well, the Hawaiian Volcano Observatory was established way back in 1912, and today they deploy an absolute arsenal of cutting-edge technology. They aren't just sitting around waiting for lava to appear. They're actually detecting subterranean swelling deep underground. By using networks of highly sensitive GPS stations, tilt meters that measure the literal physical bulging of the ground, strain meters, summit gas detectors, and massive seismic networks, scientists can track the deep rumblings and pressure buildups months or sometimes even years before an eruption actually happens. Which really leaves us looking toward the horizon, because tectonic plates never, ever stop moving. In about 500,000 to a million years, Mauna Loa is going to drift away from its life-giving hotspot entirely and become completely extinct. But what about the immediate future? We know that deep fault lines exist right under the mountain, and we know from the geological record that a sudden, massive collapse of the volcano's flank could trigger a staggering ocean-crossing megatsunami, just like the ones that actually struck the Hawaiian Islands hundreds of thousands of years ago. So the giant is back asleep for now, but as we've learned, geology is never truly still. What secrets is Mauna Loa going to reveal the next time it wakes up? Well, I hope this explainer sparked your curiosity to find out. Thanks so much for joining me, and keep learning.